Welcome back to Calculus 2. In this video, we're going to talk about graphing polar coordinate equations. Kind of the second half of really our introduction to polar coordinates. After this, we'll actually get into some calculus with polar coordinates. A lot of times you get introduced to these coordinates much earlier, sometimes in trig. Honestly, you could really talk about them to a certain extent even in college algebra. But we're talking about them here. So, some different things to consider when you're graphing. Symmetry is very helpful. If you want to test the different types of symmetry, you have symmetry about the x-axis if having a point r theta implies the point r negative theta is also there. So, if replacing theta with negative theta has no net effect, it's symmetric about the x-axis. Or replacing theta with pi minus theta. And if you can replace both r and theta with negative r and negative theta, it has no net effect on the equation, then it has symmetry about the y-axis. If you can replace just r with negative r, it has symmetry about the origin. So let's do a little bit of work. Let's do this. So we're supposed to sketch in the xy plane and determine symmetries. For some reason I apparently forgot to write that down in... It's the same plane in both polar and Cartesian coordinates. It's just your measurements in it are a little bit different. But let's see here. Sketch in the xy plane. So let's talk about symmetries. If I replace r with negative r, I don't think I'll get the same thing, because how about theta with negative theta? Both, I don't think, would be quite the same either, because if I replace both, negative r is 1 plus 2 sine of negative theta. You can pull a negative out of a sine, minus 2 sine theta. But then if I divide by the negative, I would get r equal negative 1 plus 2 sine theta, and that's not the same thing. So I don't think this has any of the symmetries. Let's actually look at it. It's pretty easy to do graphs in polar coordinates. You do have to be able to solve for r to do it in your calculator, but I think we can do that. You just have to go into mode and then go over to polar mode. Hit that. So r1 is 1 plus 2 sine of theta. Let me graph this. Yeah, that looks symmetric about the y-axis, though. Huh. Let's go look at our slide again. Symmetric about the y-axis if negative r, negative theta lies on the graph. Oh, I really kind of misinterpreted that. It's either or of those, so they could... One of them apparently could not be true, but the other one could be. So if I replace pi with pi minus theta, so if I look at this, r equal 1 plus 2 sine of pi minus theta. If I think about that, sine of... So here I've got theta. Right. Pi minus theta. Oh yeah, pi minus theta would also be up here. And similarly for that. So yeah, that's not going to have any effect on the sine, so that's going to be equal to 1 plus 2 sine theta. So yeah, it is symmetric about the y-axis. I have to remember that. It really is an or case. You really do have to check both of them. Alright, let's look at the other ones. Negative r, pi minus theta. Negative r. 1 plus 2 sine of pi minus theta. Well, that'll have the same sign, so that's the same as 2 sine theta. But then this is not the same equation. So that's out. So y-axis, not x-axis. How about the origin? The origin r theta, negative r theta, and r plus theta. So negative r. Now we know that negative r isn't. What was the other one? R theta plus pi. So if we look at r1 plus 2 sine of theta plus pi, unfortunately that will change the sign of this, because looking at that, if here's theta, theta plus pi is down here, which will have a negative sign. So this would be the same thing as 1 minus 2 sine of theta, which is not the same. So it only has symmetry about the y-axis. And then as far as graphing it, I mean, you can just use the calculator if you want. What I generally do is I will plot it like that, and then I will either use values myself, or I'll go in the table. Yeah, that's not super helpful to me, but like within I might say just want to do like a full rotation, like 0, sure. If I plug in, say, pi over 2. Oh, that's right, I can't type in yet. I gotta change it to independently's ask. So table, 0, pi over 2, not e, pi over 2, might as well do pi over 3 as well. If I can somehow type the pi. And it's symmetric about the x-axis, so I really don't have to go past pi over 2. So let's do pi over 4 as well. Alright. So, if you wanted to sketch this, here's our point table. R theta. So it's 0, it's 1, at pi over 2, it's 3, pi over 3, it's about 2.73, at pi over 4, it's 2.41. So, get our graphing background out. So, 0, 1, it just depends on how big you want your units to be. I will make 2 of these be 1, so this is 1, 2, 3, 1, 2, 3. So then, 0, 1, pi over 2, 3. So, at pi over 2, we're all the way up here. At pi over 3, let's see, pi over 4 first, because that's this angle. We're at 2.41. So that's, let's see, 2.41. I think we're about, so this is about 1.4. This is about 2.8, so 2.41. It's about right there, I think. And then pi over 3. Let's see, that's about right here. That's 2.73, so that's a little bit further out. About right there. So we're looking at here. I'm not sure what the little divots near the middle come from. Let's zoom in a little bit. Oh, that's cute. So in between that and that, you get a fair amount. Let's see. So let's trace. It does this extra little loop-de-loop. Let's see. Let's see. Pi is probably where it actually hits 0. Pi is right there. And then between pi and 2 pi is where it does this stuff. That's interesting. So yeah, rotating around, we kind of, you know, we have our similar points over here. And then it goes down and does this business. So yeah, it's a pretty neat little graph. Let's see if I can make the inside of that just a little bit nicer. This goes down, oh, just a tiny bit. It's much less than I have graphed there, probably. It's 1/10 of a unit. So this is 1/2 of a unit, so 1/10 is about a, oh, I guess that's not too bad. That's not too bad. It just goes down about that much. Then how high up does that go? To 1? So at theta is 4.71. Is that 5 pi over 6? 3 pi over 4? 3 pi over 2? Yeah, it's 3 pi over 2. Interesting. So it's basically this angle. That's where it is. It's interesting. Alright then. It's nice it gives you X and Y values to plug into as you're going. So, do. Alright then. Let's look at another one. Just going to graph this lemniscate. There are a lot of neat shapes in polar coordinates. So let's look at... First off, let's look at my window. 0 to 2 pi, that's fine. As far as graphing this one, since it's r squared, I really need to square root it, so 2 square root sine 2 theta. And don't forget, we need the negative one as well, so I'm just going to do negative vars, y vars, polar R1. Now let's see what that looks like. Oh yeah, the flower petals. Just a 2-petaler, it looks like. I suppose I should have dealt with the symmetries while we were thinking about it. So symmetry about the x-axis, it doesn't look like it from the graph, but if I replace r with, let's see here. If I replace r with negative, if I replace theta with negative theta, it's not going to be the same. It'll flip the sign of that side. If I replace r with negative r and that to pi minus theta, r with negative r isn't gonna change anything. But if I change 2 times pi minus theta, I think the 2 is going to cause a problem. If you got theta, 2 theta is going to be, could even be over here, and then pi minus that'll jump, would jump a, back to here and have a different sign. So suppose if I had something in here, pi minus theta would be here. And then 2 times pi minus theta would take me into the negatives. Be probably over in the quadrant 4. So it would not be the same sign. So it's not symmetric about the x-axis. As far as the y-axis goes, let's see. Replace r with pi minus theta. We already went through that. Negative r, negative theta. The negative theta will cause a problem. The negative r won't. Symmetry about the origin. Replace r with negative r. Yeah, that'll work. Replacing r with negative r will do nothing because it's squared. So it's symmetric about the origin. So with that in mind, we really only have to graph one of them. So let's see here. Next. And let's grab a calculator. We're going to graph r squared. Oh, we already got that. We already got that. That's right. So let's look at the table. Trace. And really just graph one of those rose petals. So, let's say, look at our table here. Just in the first quadrant, we have 0, 0, pi over 2, 0. So r theta. 0, 0, pi over 2, 0. Pi over 4. 1.86. And 0.7854. 2. Which, thankfully, because of trace, we can actually just plot those using the x and y coordinates as well, which is convenient. So, for example, pi over 4 is just at 1.4, 1.4. So if I do this, and do the same thing before of this is 1, this is 2, so 1.4 is about right there. So 1.4, 1.4, this is 1. It's about right there. I believe that's the far edge of the flower petal. And then let's just graph some of these others. So 1.36, 0.36, 0.37. So 1.36. And then up about right there. Then look at that part. 0.36, 1.36, so it's pretty symmetric. So I mean, honestly, then I mean it's the same kind of thing out here. Can plot the points to get it there. Actually, should be quite a bit. Have the tip down there. Yeah. And you'll see some things that have all 4 rose petals and etc. And the last thing we're going to talk about a little bit in this section is just slope of the curve, the derivative in the xy plane. It's not hard to derive this. We know from our parametric equations that if we write in terms of theta, if we want to write dy dx, this is the same thing as dy d theta over dx d theta. And we know from the last section that is the same thing as the derivative of r sine theta over r derivative of r cosine theta. Now r is probably a function of theta itself, so we do have to use product rule up here. That becomes r prime sine theta plus r cosine theta. And then on the bottom, that becomes r prime cosine theta. And then derivative of cosine is negative sine, so minus r sine theta. And that's where they get this. They're just using f of theta in place of r. But it's that equation. So with that in mind, we could also say find the slope of the tangent line at a point just by using that. So I'll go ahead and do that in a quick problem. But we'll leave off after that. Alright, in this problem we're finding the slope of the curve. So find the slope of the curve at the given value of a, at the given value of theta. It also wants us to sketch it. We'll take a look at the sketch, but I don't think we'll actually do this one by hand. We have r equal -1 plus cosine theta. They actually tell us this is a cardioid. That means it's heart-shaped, not heart as in, you know, like Valentine's Day, but heart as in the physical organ. Theta is plus or minus pi over 2. Alright, so if we're going to calculate dy dx, we already saw that was dy d theta over dx d theta, which came out to be r prime sine theta plus r cosine theta over r prime cosine theta minus r sine theta. Alright then, so r prime is going to be negative sine theta. So we gotta actually be able to plug in r and r prime now. So that is negative sine squared theta plus -1 plus cosine theta times cosine theta over negative sine cosine minus -1 plus cosine times sine. Let's see here, that is negative sine squared. 2 got a little bit low there, but it is meant to be a square. And then multiply by cosine through, you get minus cosine, and then plus cosine squared. Over negative sine cosine. Alright, I can basically just flip both those signs, so it'll be plus and minus. So it'll be plus sine theta minus sine theta cosine theta. So on the bottom, we've got sine theta minus 2 sine theta cosine theta. And on the top, and you might say this is negative, 1 minus cosine squared, so it's -1 plus cosine squared, which then would combine with that one, you get 2 cosine squared minus cosine theta minus 1. I don't know. In any case, I suppose I better just go ahead and plug in at this point. I can factor the top, but I can factor the top and bottom, but I don't necessarily know we're going to get very far with it. Let's see, 2 cosine theta. Cosine theta. Have to be 1 and 1. minus and plus, that's true. And on the bottom, you got sine theta times 1 minus 2 cosine theta. Yeah, nothing's going to reduce, so it's kind of pointless. But let's see, cosine of pi over 2 is 0. So this is 1 times negative 1 over sine of pi over 2 is 1. 1 times 1. So that is negative 1 at pi over 2. At negative pi over 2, cosine is still 0, so we still get 1 times negative 1, but sine is negative 1. So this one, we will get positive 1 as our slope. Let's take a look at those graphs. It's negative, I need to be in polar, let's see, polar mode. Negative 1 plus cosine theta. Then let's take a look at the window. 2 to 2 pi is fine. You don't need to get very far out on this because the absolute maximum that gets is negative 2. So let's say negative 4 to 4 on both. Yep, and there's your cardioid. You can tell then at pi over 2, which I believe is right here, has a slope. Well, let's see. Let's make sure. So it seems like it went backwards, didn't it? Pi over 2. Yeah, pi over 2 has a slope of negative 1, just the diagonal. At 3 pi over 2 and negative pi over 2 is this one. And that has a slope of positive 1. You can tell it's going up. Alright, so that'll be it for this section. Next time we will actually do some more calculus with polar equations, specifically looking at doing some more arc length and different things. So it's very similar to what we did in section 11.2 when we were doing calculus with parametric equations. We're just specifically going to focus on polar form calculus. See you then. Have a great day.